Welcome to AP Chemistry Unit 9, Thermodynamics, Applications and Electrochemistry. This is the ultimate comprehensive review covering all topics of Unit 9 from 9.1 till the end. Over the next 3 hours and 36 slides, we will master entropy, Gibbs-free energy, equilibrium relations, coupled reactions, electrochemistry, cell potential, Nernst equation, and Faraday laws of electrolysis. We've organized this into 6 modules with 6 slides each, packed with dense content, equations, worked examples, diagrams, and pro tips. By the end, you will have completely mastery of thermodynamics. Let's dive in. So let's start with topic 9.1. This is the introduction to entropy. What is exactly entropy? Entropy, which is symbolized by the capital S, is a measure of disorder or randomness in a system. The more disordered a system is, the higher its entropy. This brings us to the second law of thermodynamics. The entropy of the universe always increases for spontaneous process. Mathematically, the delta S or the change in S or the change in entropy of the universe must be greater than 0 for any spontaneous change. Let me show you visually. Imagine that we have 9 particles on the left. They are arranged in a perfect 3 by 3 grid. That's low entropy. Why is that? There is very minimal disorder. They are organized. There is no chaos. On the right, those same 9 particles are scattered randomly. That's high entropy because there is more disorder. The system naturally moves towards the disordered state. But why is that? There are more ways to arrange particles randomly than in a perfect grid. Boltzmann equation captures this. We don't need to know the Boltzmann equation very well in the AP chemistry, but it's good to understand the idea that S is equal to K times the natural log of W. What is K? This is Boltzmann constant. W is the number of microstates. What is microstates? The possible number of arrangement. The particles can be arranged this way, this way. More microstates means higher entropy. A practical example: when a solid melts into liquid, then evaporates again to gas, the entropy will increase at each step because the particles become more disordered and have more freedom to move. So let's dig deeper into the microstates to understand what is the meaning of microstates. We hear this word a lot in the class. A microstate is a specific arrangement of particles or energy in a system. So think about flipping 3 coins. The possible outcomes are head, 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 tail, head, tail, head, head, tail, tail, and so on. That's total of 8 microstates. So W, or the number of microstates, will be equal to 8. But if we use the equation, the S is equals to K ln W, where K is the Boltzmann constant, 1.38 times to the negative of 23 joules per Kelvin. This is a constant. The more microstates available, the higher the entropy. The total S will be at the end is higher. Here is the key insight. Systems naturally evolve towards states with more microstates because those states are statistically more probable. So it's highly probable that you will come to a microstate of disordered form, then going back to the ordered form, because this is only one state or one case. Imagine 2 gas particles inside the box. If they are stuck in one corner, this is only one microstate. That's W equal 1, very low entropy. But they can be anywhere in the box. They can be endless arrangement of these particles. This particle can be to the right, this one to the left, this one come to the left, and this to the left also, while others on the right. So different microstates. This is very big number of possible positions. So W is huge, entropy is very high. So the nature always favors the high entropy state because it's overwhelmingly more likely to happen. Now the second law of thermodynamics tells us delta S universe is greater than 0 for all spontaneous process. But what is the meaning of spontaneous process? A spontaneous process is a process that will happen on its own. Here is a breakdown. The delta S of universe equals the delta S of my system plus the delta S of the surroundings. You need to check both. So there are three possible scenarios. Scenario one is the delta S of the system is positive, which means that my system entropy is increasing. The delta S of surroundings is negative. You must check the total because if the sum is positive, it's going to happen. It's a spontaneous process. Two, delta system is negative and delta S of the system is negative and the delta S of surroundings is positive. Again, check the total. The third case, both are positive, and this means that it's anyway gonna be positive because this is always spontaneous because the reverse entropy definitely increases. So let's do a worked example. I have some ice melting at 25 degrees Celsius. The delta S system equals positive 22 joules per Kelvin because ice becoming water increasing the disorder. The delta S surroundings equals negative 19 joules per Kelvin because the surroundings lose heat to melt the ice. But the total delta S universe equals positive 3 joules per Kelvin, so melting is spontaneous at 25 degrees. A common mistake, students think negative delta S of the system automatically means non-spontaneous. Wrong. Always check the surroundings too. But now let's calculate the entropy changes quantitatively. Every substance has a standard molar entropy, S0, measured at 298 Kelvin and 1 atmospheric pressure. The units are joules per, sorry, the unit is 1 atmosphere. The units are joules per mole Kelvin. So watch these units. To calculate the delta S 0 for a reaction, that's called delta S node. Use delta S node of reaction equals to the sum of number of moles of S node of the products minus the sum of the number of moles of S of reactants. Just like Hess law for the delta H I'm using, I'm doing the same for delta S. So calculate the delta S node for the reaction 2H2 plus O2 give us 2H2O. Given the data, the S node of H2 is 131 joule per mole Kelvin, and that of oxygen is 205, and that is 0 for liquid water. So S node for liquid water is 70. Calculation product side, 2 moles. Don't forget the number of moles. Multiplied by 70 minus 2 multiplied by 131 plus 205. And S node of liquid water is 70, right? So 140 minus 467 equals to negative 327 joule per Kelvin. Negatively, why? Because we are going from gas to liquid. So that makes sense, right? Going from gas to liquid means that the entropy is going to decrease. That's why it's a negative entropy coming minus 327. So the key trends to remember for the entropy is that the S of gas is always way greater than the S of liquid, which is greater than the entropy or S of solid. Larger, more complex molecules have higher entropy. Reactions that produces more moles of gas increase entropy. So now we have a summary of module 1, the entropy foundations. Let's recap. This is the foundation. So here is your master checklist. Check 1, can you define entropy and state the second law? Check 2, can you calculate entropy using Boltzmann equation? We said that this is not required with us. Check 3, can you calculate delta node, S node reaction from standard molar entropy values? Check 4, can you predict whether entropy increases or decreases based on phase changes, mole of gases, and molecular complexity? The mole of gases increases, the entropy increases because there will be more microstates. And if the molecule is more complex, then the entropy will increase. Your master equation for module 1 is, we will ignore this equation, then we have the delta S node of reaction equal to delta S node of products minus that of reactants, the sum of course, and delta S of universe equal to delta S of system plus delta S of surroundings, which must be always more than 0. So we'll do a quick self-check. Ice melting, is delta S positive or negative? 2NO2 give us 2NO4. They will combine to form 2NO4. I'm helping you with the answer. Delta S is positive or negative. Is it increasing or decreasing? If it's increasing, is positive. If it's decreasing, is negative. Why does entropy increase with temperature? So let's see some common mistakes. Don't forget that gases have much higher entropy than liquid or solid. And watch your units. S0 is in joules per mole Kelvin, not kilojoules. Next up, module 2, where we will tackle Gibbs free energy and learn how to predict if the reaction is spontaneous or not.